Yeah, hello, everybody. First of all, I would like to thank the conference committee to invite me here. It's a very great honor to be here. And it is very nice conference and a very beautiful city. So I will talk about the content simulations, the topic. In the last 2 days, I think you already have many talks and posters on this topic. And today I will continue this with these nuclear spins. Yeah, first of all, as you know, the spin is an intrinsic property of the quantum mechanical particle, and it's widely used in the quantum information processing architectures. So here I just show some architecture here, and I think still has many different physical systems use these spins. So the spins. Why we use these spins in quantum information processing? The spin, one thing is the spin can be easily manipulated by the major magnetic resonance techniques. For example, if you use these nuclear spins, you can use this NMR nuclear magnetic resonance to operate that. And also, for the nuclear spins and electron spins has different properties we can use. So many hybrid quantum information processing built up with this nuclear spins and electron spins. So the spin-based quantum information processing is one of the most successful physical implementation and provides the inspired technology for the other solid state as an important test bed for the developing quantum control method. So for what are doing, so we just focused on these spins and use this spin magnetic resonance to do many different topics in the quantum information process. For example, quantum control, quantum simulation, and quantum metrology, quantum algorithm, also the quantum magnetometry. So this is what we'll do in general, but in this talk, I will focus on this quantum simulation topic. And also, we use this platform is nuclear magnetic resonance, and we will use these physical systems to simulate different quantum spin models. For example, quantum IC model and X model, or the topological order model, something like that. We use these quantum simulation techniques. We can study many different complex many-body physics. For example, the quantum phase transition, the topological order, or also we also investigate these out-of-time order correlations. I will give some introduction of these different kind of things. So first of all, introduced simply our experimental setup. So we use these MR things. So the MR quantum register is we use these spins, nuclear spins in the molecules, the different molecules. So if you have this nuclear spin 1/2 particles, and if you put this in the magnetic field, you have this spin up and spin down. So we can use this as qubit. And how to control these spins? So we use these radial frequency passes and to operate them. And we use these spin-spin interactions to go to these non-local operations between different spins. And for these initialization things, we use this technique, so many years ago, proposed this pseudo-pure state techniques. For the readout, for the MR systems, we use this ensemble weak measurement for that. So here, I just show the basic Hamiltonian on these MR systems. So this is Zeeman interaction with this static magnetic field. So use these things, we can individually address different spins. And for these interactions, in the liquid state MR, so for this dipole coupling is average 0, and we have no, if you use this spin half system, nuclear spins, we have no these quadruple interactions. So only left is just the J coupling between each spins. So we can use these J couplings and to do this non-local quantum gates, something like that. So to control these things, we use these RF passes. Of course, every physical systems, we have this relaxation, that means decoherent things. So also we can think about these relaxation things in our experiments. Okay, so here I'll just show some example how to control in the 2-qubit systems. I will not go to this detail, just give this slide to show this basic concepts. And of course, for each experiment, we have to do is we should improve our precision of quantum control. Otherwise, you cannot achieve the successful experiment. So in our experiment, in our lab, we also always improve our techniques on the quantum control. For example, here, this is just the concept how to control these nuclear spins in MR systems. This is molecules, we have different spins each other and have the interaction between the spins. And for the traditional MR, we can use these passes, these long passes, yeah? The pass and delay, we can build up the different quantum gates, something like that. But during this progress of quantum information processing, we developed many very good techniques to how to control the spins in MR community. So for example, we can use this numerical optimization passes and to get more higher fidelity quantum control things. Okay, so come back to my talk on the quantum simulation. So here I just show the general quantum simulation scheme. So here we want to simulate maybe other systems, for example, with quantum spin models. And the physical system we use is MR systems. We have this internal Hamiltonian, we have this external Hamiltonian. So that is depending on what physical system we use. So the basic steps of these quantum simulation schemes. So first things you should get this mapping between this simulator system and the physical systems. And also, you should have to initialize your systems, and we can use different methods to do that. And also, for quantum simulation, so we should simulate the different Hamiltonian. So you use the physical systems and to simulate other complicated quantum systems. So the last things, you should extract the useful information for your problems. Yeah, so normally you can use state tomography to do that, but this is not efficient way. You always use this exponential resource to do that. So for the quantum simulation, if you only just focus on specific properties, and you can just extract maybe some properties, use this efficient way to do that. I will give some example later. Yeah, so just give the very simple example how to do this simulation in MR systems. We first studied, maybe many years ago, we firstly choose this very simple model. So this is first order phase transition models, and we have this spin model, and we want to use these MR systems to simulate this. So the things, we follow these basic steps and how to find these mappings between this model and between our MR systems. So we use this nuclear spins to mapping this spin poly matrix, this first one. And how to simulate these things, use these physical systems, and we use these average Hamiltonian series to get this simulation, Hamiltonian simulation. And of course, for the initial things, we use this adiabatic technique and to prepare the state we want. And for this, because here we have this first order, if we want to track the ground state things, if you have this energy level crossing, so that means you cannot achieve, follow this ground state by adiabatic evolution. So we use this non-Dalzino anti-crossing to do that and follow the ground, extract the ground property of these models. And then the last one, if we want to detect the phase transition, we should choose the suitable order parameters. So you can use the traditional way spin-spin correlation. But the reason, so in the counter information processing, we want to start more things on that sense. For example, you can use this entanglement to detect the phase transition things. So here, I just show how to simulate this Hamiltonian and use this MR system, this MR system, and this one is we want to simulate it. We just choose the correct suitable parameter on this in the experiment, and then we use this average Hamiltonian series, and we can achieve the dynamics of these simulated systems. Okay, so here it's just 13 years ago, we performed the quantum baby phase transition things, and we use this adiabatic quantum simulation, and we drive this system from this paramagnetic phase and go to this antiparamagnetic phase. Yeah, so that means we can see here the ground state at the beginning is just a product state, and if you're in this antiparamagnetic phase, you have this entangled states. So, and I think in 2002, and in this paper, and just show we can use this entanglement as order parameters to detect this phase transition. And this is theoretical people. And in 3 years later, and we use this MR simulator and to show we can use this, we experimentally detect the entanglement phase transition in such simple model. Yeah. So that means we simulated this a quantum magnetic. And later, because there we use this quantum state tomography and to get this coherence and entanglement things. But it's not also efficient way. And another efficient way, we can use this probable qubit, and we can detect this Loschmann echo things, and that means we can variable of this quantum fluctuation. We can also detect the critical point by this technique. Also, you can also use this geometric phase and to detect the phase transition things. So this here we just show these things in the experiment. Of course, this is the before. At the beginning, we just use this very simple experimental, very simple case, just 2 qubit. And for the quantum information things, we should increase our size, our physical system size. So, but just step by step, yes. And if we involved more particle or more qubits in the experiment, we can see many different, all very rich physical phenomena on that things. And we can also, if we use these many-body interactions inside to study, and we expect we could have the new physics inside. For example, you can go to maybe degenerate ground state, all these frustration phenomena also reach entanglement inside. So that means for our experimentalist, we also able to put the experimental physical system size larger. Yeah. So the next step, yes. For example, This is one theoretical paper also see the new physics if we involved this three-body interaction. So you can see a three-spin classical Hamiltonian will exhibit a novel kind of critical behaviors that not revolved by the traditional approach. So if you use these two-point correlation functions, you cannot detect this kind of critical behaviors. So that just means if you got this many-body interaction inside, and you can get rich physics inside. So that means for the experiment, we also want to show these things in the real experiments. So that means we experiment started this complicated Hamiltonian or things. We have these two-body interactions and we have these three-body interactions together. So of course, the three-body interactions is normally not exist in nature. So, but in the quantum simulation technique, we can use these two-body interactions to generate the three-body interaction or four-body interaction, something like that. Yeah, here it just shows the example. We use these two-body interactions to generate these dynamics of these three-body interactions, Hamiltonian. So here is our experimental result. It's just you can see here if we use this spin-spin correlation as the order parameter, and you can observe these critical behaviors on this two-body interaction Hamiltonian. But if you use the same correlation, same two-spin correlation detector, but you cannot see the critical behaviors in such model with these three-body interaction. So you can see nothing. So that means the new critical phenomena induced by the three-body interaction cannot be detected by the standard two-spin correlation. So for us, if we want to know what happens in this such model, we should choose the new order parameters. So because the entanglement is very popular in these quantum phase transition points, so we just think about the entanglement witness operator maybe is suitable for that. So that here we can show, the experiment show here, if we use these the W state entanglement witness or GHZ entanglement witness, you can see in such two models, you can see this or experimental observe these critical points or critical behaviors. Even more, depend on these things, if you know these values, you can also know what kind of entanglement or what kind of state in such phase. Yeah, so you use this entanglement witness operator, you can know more things. And go further, so if we have these four body interactions, so that is more, the new physics is more rich. So for example, if you think about this Kataev-Turcotte model and also Wien-Planck models, so that is the topological exist in such kind of models. So that means you can also study the more interesting the physical phenomena in such models. But for the topological orders, the many theoretical people with that. Also in the condensed matrix, this is new bridge of that. But for the experiment, it's very great challenge to study because for the three-body or four-body, it's not exist in real systems. Yeah, so that is mean difficult to realize topological order. But so many people looking for that at this moment. Yes. So for us, the one possibility or one solution, we can use this quantum simulator to do that. And the quantum computer provides an active way to investigate the topological order in the experiment. So that means we can use the artificial states of the matters. And yeah, so also many previous experimental for these Turcotte models. But most of the experiment is just a state-based approach. What means that? So it just directly propel the states with this topological order and then studied the property of that. So that means most of experiment not realize the Hamiltonian, exact Hamiltonian. So that means in 2014, we use this adiabatic quantum simulation, and we simulate this one-planet spin model, and we experiment observe the adiabatic passage between the different two topological orders. Okay, so that is, we show these things. But the later, we just see the more difficult things. It means how to classify the topological order. So that means for the this is the older questions, but the new object. And so also, for this topic, so many theoretical people think about that, and you can use this degeneracy or entanglement entropy or molecular transfer to do that. But the questions, how to identify the topological phase unique and purely by the experimental means. So we have started this topic in the experiment. I don't want to go more detail the modulated path matrix, but I want to give you know the story how we achieve this goal. We wanted to get this modular matrix in experiment, because if we go there and then we can identify the topological order. So that means, of course, if you can do this SST matrix, and then you can do quantum processing tomography to do that, but this is also not an efficient way. So if you observe these formula things, and maybe you can think about this interferometer method to do that. So that means this inspired us to design the scheme, the efficient scheme, how to achieve this S and T matrix in experiment using this interferometer things. So the things to achieve this goal in the experiment, we also think about that things, different three problems. And because in this node, you don't know what is ground state, you must to be prepared, and in such subspace, the ground state subspace. So we use this random adiabatic evolution, and even we don't know the ground state, what is this, but we know this Hamiltonian, and then we can use this technique and to put these system states in this ground state subspace. And of course, you must to achieve physically of this S and T matrix. So, and then, because this ST matrix is corresponding to 90 rotation or trace operation in this lattice, and then we can use this swipe gates and to do that. And for the analysis, we achieve this in the polynomial gate complicated. And the final one, we want to achieve these measurements, yes, SST matrix. So we use, as we said before, we use interferometer, and I'll also use this mathematical technology to the ground scale-meet procedure to achieve this standard basis of that. So for these things, you know, in the initial states, initialization without, so that means we use this adiabatic evolution. That means without a prior state information. Also for the measurement, without this QST, quantum state tomography. So that means the total things is just efficient. So we have this scalable quantum network to achieve these things. So here I just show the detail how to prepare this in ground state subspace. Yes, in this case. And okay, so if we go to these things, we can measure in these states in the orthogonal basis, yes. Okay, I will not go to this very detail on that things. I just gave this idea before, and I will show the, maybe I will show the last, this is our experimental systems to do that. And so this is path sequence. We use this Hamiltonian. And so maybe we go to these things. And this is our experimental result for the step 2. So that means we can reach this S and T matrix. This is experimental data in the random state basis. And from this one, so from here, and we choose these things and use this mathematical method. We can transfer this S matrix and T matrix in the orthogonal basis. And from orthogonal basis, and we can achieve in the standard basis. And then we can, from this S and T matrix experimentally data, and we can know what is phase order inside this. So from this one, we can see this Z2 terracode model orders. So what's more in systems? So because before we just say we just characterized this one in the exact cative point, but in such techniques, we can also get more things on that. We can simulate these perturbated models, and we can detect this robustness of this phase transition. And the total experimental result we can see here. So here, this is the breakdown point from that things. Sorry, how many minutes? Is already? Okay, so I just a few things. And here you can see here, this in this case, this is topological phase here. And if you change this just a local perturbation, you can know exists the topological phase is also exists in these things. Just across this point, you just see this breaking of these topological orders. So that means we can see here this experimentally conform the entanglement extended region of the phase space of this topological order. So here I just show our recently work on this topological order identification. And I wanted to, finally, I want to say more things on this OTOC. So that means at the similar thing, the same time with these trapped ions, we also use these MR simulators to measure the OTOC things. And in here, we also measure these quantum chaos in such models. And also, yeah, so that is my conclusion. Yeah, we use these liquid MR systems and do many things, and we use, now we just change the different size and different technique and different environment. We investigate many different things. And what I want to say is, and finally, is just we want to push this experiment to the large systems, and we want to, first of all, we want to do this quantum control on the large systems. And this is recent paper, we do this close loop and how to learn from these real physical systems. We can optimize the path. And we do this experimental in the 7-qubit systems, but later is very directly applied to these 12-qubit systems. And more things I want to say is recently we developed the zero field MR systems, and at this moment we achieved this benchmark of quantum control on such systems. Okay, sorry, and I would like to thank these all many different people and collaborators and the students, and thanks for your attention.